All right, now there are some fractions that we know we just can't write as decimals. For example, we cannot write 7/11ths as a decimal. Why not? Well, because there's nothing we can multiply by 11 to get a power of 10. But there's nothing physically stopping us from understanding 7/11ths to mean 7 divided by 11. What happens when we do that division? Well, let's try it and see. So 11 is going to be the divisor. 7 point is going to be the dividend. We'll have a decimal point in our answer. 11 goes into 7 not at all. So we add a 0 to the right of the decimal point. 11 goes into 70 6 times. 6 times 11 is 66. We subtract and we get 4. Add another 0. 11 goes into 40 3 times. 3 times 11 is 33. We subtract and we get 7. Oh, do you see what's happening? Add another 0, bring it down. 11 goes into 70 6 times. 6 times 11 is 66. Subtract and get 4. Add in another 0, bring it down. 11 goes into 40 3 times. 3 times 11 is 33. Subtract, we get 7. This just keeps going. This pattern repeats, we can say, forever, by which we mean until we get sick of it and walk away. No matter what, anytime we have a 6 as a digit in our quotient, the next digit will be a 3. Anytime we have a 3, the next digit will be a 6. Because of this pattern in the remainders, we have a remainder of 4, then of 7, then of 4, then of 7. This is called a repeating decimal. It repeats forever. So it repeats for as long as we care to continue writing, and then longer than that. What do we write? We write 7/11ths is 0.63 with a line over the 6-3. What does the line indicate? The line indicates that the pattern underneath repeats. We would read this as 0.63 repeating. Notice that I wrote the shortest possible pattern under the line, and I only wrote it once. There are other ways we could describe this. We could say 7/11ths is 0.6 and then 3/6 repeats. Or we could say that it's the pattern 6-3-6-3 all repeating, or other ways to describe this pattern. But unless we have some compelling reason to describe it in one of these 3 ways, these are very weird. They aren't strictly wrong, but they are sufficiently weird that they don't exactly constitute a right answer in the context of a math test. Unless we have a compelling reason to describe our number in one of these ways, this is the one that we're going to choose. Now, the thing with repeating decimals is it's very hard to see what fraction a repeating decimal represents. And partially for that reason, we prefer not to try to do arithmetic to repeating decimals. We can use them in the kind of arithmetic where we move decimal points around, but anything more complicated than that is frankly awkward. Let me show you an example of what's frankly awkward here. What if I asked you, what is 0.3 repeating plus 0.6 repeating? You might naturally say, maybe 0.9 repeating. This 0.9 repeating is actually extremely troublesome. Where do I get 0.3 repeating? It turns out that 1/3 equals 0.3 repeating. Where do I get that? Let me show you. 3 into 1 point. 3 goes into 1, not at all, of course. Add a 0. 3 goes into 10 3 times. 1 left over. And now you immediately see the pattern of remainders repeating. At each stage, we're going to say 3 goes into 10 3 times. So 1/3 is 0.3 repeating. It also turns out that 2/3 is 0.6 repeating. I'm going to have you pause the video and try that division. Pause the video now. We see 3 goes into 2 point. 3 goes into 2, not at all, so we add a 0. 3 goes into 20 6 times. Since 6 times 3 is 18, we subtract. 20 minus 18 is 2. Add another 0 and bring it down. And again, we immediately see the pattern of remainders repeating. At each step, we're going to be saying 3 goes into 20 6 times. So the 6 will repeat. All right, how is that relevant to our original question? 0.3 repeating plus 0.6 repeating. That's 1/3 plus 2/3. 1/3 plus 2/3, that's 3/3, which is 1 whole. 0.3 repeating plus 0.6 repeating, in fact, is 1. But you wouldn't immediately see that by looking at this notation. It's only clear when we're looking at the fractions. So it's for this reason, as much as anything, that we will prefer to do arithmetic with fractions and only write repeating decimals when necessary. Nonetheless, it's nice to be able to write these repeating decimals when we need them, so I'm going to give you one of these to practice. Noticing that 12 has a 3 in its prime factorization, and therefore 5/12 can't be written as an ordinary terminating decimal, that is, a decimal that doesn't repeat. Write 5/12 as a repeating decimal. Pause the video and try this now. All right, so we're going to divide 12 into 5 point. 12 doesn't go into 5 at all, so we'll add a 0 after the decimal point. 12 goes into 50, I think 4 times, since 12 times 4, that's 48. Subtracting, I'll get 2. 5 and 2 are different. We aren't getting that pattern of remainders yet. 12 goes into 20 only once, since 1 times 12 is 12. 20 minus 12 is 8. 5, 2, and 8. No pattern of remainders yet. Bring in another 0. 12 goes into 80. I think 6 times. 12 times 6. 6 times 2 is 12. 6 times 1 is 6, plus 1 is 7. Yes, that's going to go in 6 times. 6 times 12 is 72. The remainder is an 8. There we go. I see it. This remainder 8 has repeated. So that means from now on, every time I divide, I'm going to be dividing 12 into 80. The answer will always be 6 and give me a remainder 8. So the 6 is going to repeat. The 1 and the 4 do not repeat, only the 6. So I get 5/12 is the repeating decimal, 0.416 repeating.